Good afternoon, everyone. I am Quah Beng, and for this session, I will be presenting on 3D visualization of subsurface channels for rig entry operations. Within the Asia-Pacific region, jackup rigs remain the primary choice for drilling shallow water wells due to its relative low cost and availability. Successful emplacement of a jackup rig onto a predetermined location requires a geophysical site survey to assess the on-site geohazards, to make sure the location is clear from seabed anomalies such as depressions or scarps and/or debris items that may damage the jackup legs during the spud. The subsurface lithology should also be generally flat to prevent instability, which may result in damage to the legs, the structure itself, or even the loss of the rig. Ideally, there shouldn't be any challenging subsurface geology to contend with, but unfortunately, this is not usually the case. There are often times when the situation calls for siting a rig on top of a channel. Is it safe, and has it been done before? Yes, it is actually relatively common and acceptable, but if we had to put it on top of a channel, it's generally advised to put it near the base of the channel and have leg penetration analysis done. The reason for this is that a channel generally has a higher slope angle near the edge of its flanks and lower slope angle near the base. The sedimentation above the base of the channel is also more homogeneous and a more consistent lateral formation strength compared to the flanks. So, the current practice for site surveys is to map the edges along the top of the flanks and also the base of the channel. Generally, this should be sufficient to get a location approval, even though there are some missing details of the channel. How steep is it along the channel flanks? How far does it extend? And any lateral changes within the channel would not be captured. For complicated channel systems, contour within the channel would allow for some of these questions to be answered. Yet it is difficult, even with a colored map, to visualize how the channel is in the real world setting. Now, how are we going to be able to improve on this? On a map, the conventional way is to plot the edge of the flanks and base of channels. The spot depths along these lines are also plotted to show how deep the currents of the channel. To have the details of the channel itself will have to be interpreted and digitized. The points shown here represent the depth of the points that are tagged along the channel, as observed from the sub-bottom profiler data. These points are then gridded into a surface that represents the channel. It is obvious that denser line spacing and closer interpretation peaks would reduce interpolation uncertainties and have improved results. Put the surface onto a 3D frame and we have this, a 3D visualization of the subsurface channel. Immediately, some things become obvious, much more than if this was just a map with contours and a color map. The base of channel is irregular. The jackup rig legs are on the flanks of the channel and there's a big hole at the base of the channel nearby, so it could have been much worse. With this, management can make informed decisions quickly and confidently and mitigations put in place with considerations of the expected hazards. Shown here is the color banding for depth, but it can be easily switched to a traffic light scheme to highlight the critical angles to avoid. This actually happened to one of our more recent operations. The jackup was to spud beside a platform which was situated at the base of a very large channel system. When it tried, it encountered issues on the starboard leg, and despite their best efforts, was unable to get a firm and stable emplacement, and came very near to having an incident with the platform. In the end, the operation was aborted and a post-mortem was carried out. Only when the channel was properly mapped and modeled out that it became painfully obvious that the starboard leg was not on a relatively flat surface but was on a slope. So, in visualizing a channel in 3D, it allows us to have a better understanding of the channel. This, in turn, gives us the opportunity to make informed decisions and plan for mitigation as required. It is also not something that is highly difficult or requires significant investment to put in place. In fact, most survey contractors within the region would be able to do it with their current technology and skill level. However, the limiting factor is our survey lines are not very dense. Interpolation of data over very large distance introduces significant errors into the interpretation. Also, the quality of interpretation is a big factor as different geos may interpret a set of channels differently, especially in data with marginal quality. Alternatively, with the advent of 3D UHR, shallow seismic has significantly improved resolution compared to the conventional 3D. With lateral interpolation reduced, this allows for channels to be mapped more accurately and in greater detail. Unfortunately, this technology is also more costly, takes longer to acquire and process, and is not as widely available compared to the standard 2D site survey. Nevertheless, it is an exciting technology that shows a lot of promise. In conclusion, 3D visualization of shallow channel systems can be an effective tool to better understand and deal with potential hazards posed to jackup re-entry. However, there has to be considerations on acquisition parameters, interpretation quality, and the processing steps involved. Denser survey line and closer interpretations are required to get a more accurate picture of the subsurface channels being mapped. And most of all, it needs to be stressed that no matter how accurately the channel can be mapped, it is not a substitute for geotechnical assessment. And with 3D, mapping channels has never been easier or more accurate. And with that, we have come to the end of my presentation this afternoon. Thank you very much for your attention.